Well, welcome to mini lecture number 6. Today I'm going to be talking a little bit about periodic boundary conditions. I got a lot of great questions about this when you were doing assignment number 3, and I was asked by a number of people to sort of talk through how we might think about these boundary conditions when we actually go to use them. And I have a little bit of joke on this title slide because periodic boundary conditions are always interesting, but they turned out to be kind of interesting when string theory was really hot. Not the string theory where we're looking at the dynamics of a string, but the string theory in particle physics. Anyway, so the picture that we have with periodic boundary conditions is that we have some sort of compact domain, meaning that I don't have the real line. I just have I have some segment that goes from 0 to L. And if I have a field, phi, defined on that segment, the requirements for that field are that everything that happens at 0, right, everything that happens here also happens here, right, that the function is continuous at 0 and at L, and that the derivative of the function with respect to space is continuous at 0 and L. Meaning that this is sort of the asteroids problem. Asteroids was a video game when I was a kid, right? Maybe you've played it. You know, you fly off one end and you come back the other end, right? The universe in that game is continuous as you go to the right on the screen. Once you leave, you come back on the left. You keep going to the right, and therefore everything has to be continuous across that boundary. That's really the same thing as saying I'm going to take this real line and I'm going to map the x equals 0 and the x equals L so that it looks like a circle, right? And there, my boundary, or my boundaries from before, now are actually at the same point, right? And so if I try to draw some function around the circle, then it really makes sense why the function and its derivative have to be continuous at that point, because they're really the same point, right? And so the algebraic expressions that I have for my field are that the value of the field at all moments of time at x equals 0 are equal to the values of the field at all moments of time for x equals L, and that d phi dx at x equals 0 for all values of t are equal to d phi dx at L for all values of t. Okay, and this is again two algebraic expressions, right? These are two algebraic conditions, the same like I had for Dirichlet or Neumann boundary conditions, except they're just a little bit different, right? Where I don't know what the value is at a particular point, but I do know that the value has to be the same at two different points. Okay, so we can go through some of the algebra that we did for the other algebraic conditions. We're going to guess some solutions, or we're going to guess that phi is made up of two different terms. Here, it's the same magnitude of k, right? And that means I'm really looking for some mode that's oscillating at some fixed frequency, right? Because of course, omega is equal to I'm going to forget the c. K, let's see, inverse meters. So if I want a meters per second, I have to divide by c, I think. Inverse meters divided by meters per second gives me seconds. Great. Okay. No. Okay, so that's wrong. So let's get rid of that because omega must be equal to k times c. Because then the c is in meters per second, and that's going to give me hertz on the left-hand side. Okay, right. So I'm looking back to my story. I'm looking for a solution, right, that has a fixed omega, right? I'm looking for a mode, right, which we've always searched for things that have the same what part of the system is oscillating at some fixed omega. And therefore, I know that there are going to be two possible values of k, right? Because it's the square root of the dispersion relation, and therefore I can choose the positive and the negative signs of k as both parts of my solution here. Okay, that was a long-winded recovery of my logic when I sit down to think about why I'm going to be using these solutions. Okay, so and again, this is evaluated, of course, at t equals 0, right? Because I'm doing this initial value problem where I'm deconstructing the solution on the initial surface, and so I'm really looking for the solutions to the spatial shoe, right? I'm looking for the solutions to the spatial part of the situation. So here I'm going to say that phi of 0 is equal to phi of L. And it's not going to look quite as pretty as before, right? Because I have 4 terms, right? I have 2 terms on the left-hand side and 2 terms on the right-hand side. So the expression that it looks like I get when I set x equal to 0 is that a plus b is equal to, on the right-hand side, a e to the I kl plus b e to the minus I kl. Whoops. And I'm just too used to writing x, okay? Now, I can do some algebra on this to put all the a's on one side and all the b's on the other side. This is just a way of thinking about how I'm eventually going to combine this with my other algebraic expression. So on the left-hand side, I'll have a times 1 minus e to the I kl is equal to, on the right-hand side, I'm going to have minus b times 1 minus e to the minus I kl. And it looks funny why I write it in this way, but I think it'll make sense once I start to do the algebra. I've done this before, right? And so I can do this algebra with a little bit of an eye towards the future. Okay, to do the derivatives, well, it helps me to just take the derivative of this function quickly so that I know exactly what I'm plugging in, right? And so this is ik times a e to the I k x, right? I'm not evaluating it anywhere, I'm just taking the derivative. The second term, when I take the derivative with respect to x, it's going to bring out a minus ik, but I'm going to factor one of those out, so it's going to be minus b e to the minus I k x, okay? So now phi prime of 0 is equal to phi prime of L. And this is going to give me the algebraic expression that now ik times a minus b is equal to ik times a e to the I kl minus b e to the minus I kl. And now you can see that it was with some foresight to this expression that I knew these minus signs might be useful. All right, so the IK's cancel. That's wonderful. I'm going to group things back together. On the left-hand side, again, I have a times 1 minus e to the I kl is equal to, now when I move the b over, right, I get just a positive b times 1. And I still have, let's see, so I have a positive, but there's this thing here still has a negative sign, right? And so I end up with what looks like minus e to the I kl. And at this point, you should look at this expression, right? Algebraic expression number 1 and algebraic expression number 2, and you should say, geez, Tom, I have a lot of anxiety over this because it looks like these two things are saying exactly the opposite, right? It looks like a is equal to minus something and a is also equal to plus that same thing, right? And you say, how can that possibly be true? Well, you actually know that possibly be true. Good. Okay, so you know that can be true because if I set the two left-hand sides equal to each other, I get that b times 1 minus e to the I kl is equal to minus b times 1 minus e to the I kl, which means that if I cancel out the b's, right, that these two things have to be equal to each other. So let me again do the algebra, right? So I'm going to move the 1 over, so I get 2. I'm going to move the e to the I kl to the other side, right? And I'm going to get 2 e to the I kl, or 1 is equal to e to the I kl. And now what seemed like a total contradiction turns out to be absolutely fun to solve, right? Because I know that e to the I kl can be equal to 1, right? And if I look back at that expression, the only time that two numbers can be equal to each other with a minus sign is if they both happen to be 0, right? And that means that e to the I kl has to be equal to 1, which means that kl is equal to some integer times 2 pi, which means that k is equal to 2 pi over L, right, times some integer. And there I get my quantization condition, right? I know now what values of k can exist, and that there is an integer number of them, and that's how they're indexed. Okay, so to find the mode functions, what I want to do is I want to go back to one of the algebraic expressions that we had at the beginning, and that is that the function itself is continuous when phi is equal to 0 and when phi is equal to L. And of course this means that a plus b is equal to a e to the ikl plus b e to the minus ikl. Of course, we just learned that kl is equal to 2 pi n, which means that e to the ikl is equal to 1 and e to the minus ikl is equal to 1. And I'm left with the algebraic expression that a plus b is equal to a plus b. Well, that's not helpful, right? A and b can literally be anything. I know, because these are solutions to a spatial, version of the shoe, that I have to have two free parameters, right, in my answer, and so they just are a and b, right? Like, that's a fine choice of parameters here. This boundary condition actually allows us to write our solutions in many, many different ways. And that varies from what I saw when I was doing the Fourier transform with Dirichlet boundary conditions, for example, because there it was very natural to have, say, when it was from 0 to L, to have the signs as the solution to that, because the sign goes to 0 at two different places, right? Here, there seem to be a whole family of different choices that you can make for the different basis functions, because a and b can be anything, right? The traditional choice, or the historical choice, is to say that I'm actually going to build my functions not with a and b, but with some linear combinations of a and b that just allow things to look a little bit more familiar. Okay, and so to build the bases here, we're going to take a and b. And we're going to split them up into sort of the solution where a equals b and the solution where a equals minus b. Okay, and the reason for doing that, and I guess there's probably a beautiful and elegant way of saying this, but I'm gonna do it sort of in a not so beautifully and elegant way, but 2 pi over L times n x plus b e to the minus I 2 pi over L n x, right? These are our functions, right? This is what my solution looks like, and actually I could just leave it like this, right? Because then I have two unknowns, a and b, and it looks like the complex parameterization in space, and therefore I could take the real part, and then I could this would just be beautiful. Okay, but I could take this and I could choose a new a and a new b, right? Such that I rearrange the parts of e to the ikx. In other words, I use Euler's formula on this, right? And I get that a cosine 2 pi over L n x plus I a sine 2 pi over L n x, and then plus b, I can't believe I wrote an e, b cosine minus 2 pi over L n x plus b sine minus 2 pi over L n x, right? And then I can use the symmetries of cosine to just get rid of that minus sign, and I can use it to change this to a minus sign and change that to a plus sign, right? Because sine is odd and cosine is even. And of course I forgot an I, but I'm going to throw that back in here. And then if I rearrange this, I can group all of my I see that there are two things that go as cosine, right? I have an a plus b that then goes as a cosine 2 pi over L n x, plus I have an I times a minus b, that's a sine 2 pi over L n x. And so I can also see that the cosines and the sines make up an equivalent set of basis functions, right? And this is confusing because for every value of n, I now have two basis functions. It really means that, I still have a countable number of basis functions, although for a given n, the way that we've defined the quantization condition, I have two different choices. and therefore I can call this something like, and just to be to be fair on ourselves in what I'm going to say in the future, I'm going to call this B sub n, and I'm going to call this A sub n, and I'm going to throw tildes on them because right now this A sub n and B sub n are just my are coefficients that I have to use to normalize these basis functions, right? But I can see that for the periodic boundary conditions, using sines and cosines as the basis for my basis is a pretty good choice, and one that historically is a good choice for us to use. So I'm going to save you the algebra of watching me do the normalization, because I'm just, I'm doing the same trick that we did with the other transcendental functions, and in order to write them as a good orthonormal basis, I know that I have to solve for those coefficients in front. But I now get that my family of solutions, and I'm writing it now as just phi of n, right? Because for every index n, I have two different basis functions. Is going to be made up of a sine part, and that normalization, that constant I need for normalization is the square root of 2 over L, and a cosine part, and therefore I'm set up now to do the Fourier trick on these, right? Because I have a good basis. It's now made of sines and cosines rather than just sines, but I can do the Fourier trick on this to try to now solve for some generic initial conditions. The only problem is that I have to do the Fourier trick twice, right? Because I, even though for every value of n, right, which corresponds to some value of k, which corresponds to some value of omega, I actually have two independent basis functions that have that same omega, right? It's kind of like having two modes at every frequency. Then I have to think about the Fourier trick as something that I have to do twice. Once to solve for the coefficients in front of the sine, and once to solve for the coefficients in front of the cosine. And so I can think about it not just having one basis, but as having two bases, where my little a sub n basis vectors correspond to the sine, and the little b sub n basis vectors correspond to the cosines. Okay, and again, using Mathematica or exact integrals or however you want to do it, you can verify that these all together make up a great basis, because a sub n, a sub m is proportional to a Kronecker delta, the same with b, but if I try to dot an a with a b, I also get 0. And so this entire family of solutions make up a good basis vector, because I really always get 0 unless my dot product between two basis vectors is exactly the same basis vector, right? Whether or not and that means that in order to not get 0, it has to be the same n, and it has to be from the same family. So I can show you this for one choice. So if I have some function, some initial condition f of x, and I want to find out, say, the a sub n's, I would do the Fourier trick by taking the dot product with a sub m, right? A sub m over here, a sub m over here. In this case, the second term just totally goes away because it's always equal to 0. This gives me my Kronecker delta. The Kronecker delta collapses my sum to just be, just to pick out the n equals m term, and I get that a sub m is f of x dotted with a sub m, right? And I can, and of course, if I use my definition of the dot product, this means that this is the integral of a sub m, which is 2 over L times sine 2 pi over L mx times f of x dx from 0 to L is equal to a sub m, right? And I can do the same thing now if I wanted to find out what the b sub n's are, the b sub m's are. If I wanted to find that family of b coefficients, I would do the Fourier trick, but I would do it by dotting in with a basis vector little b sub m. Okay, well, this turned out to be a longer video than I had planned, but I think it was interesting, and it showed us that in this periodic boundary conditions, I get a nice quantization condition, and I have two mode functions for every value of omega. And it's also interesting because this is really how Fourier series began. The story goes that Fourier was thinking about metal rings, and if you heat one side of a metal ring, say, you have a really interesting function of temperature as you go around the ring, but that function is forced to be periodic, right? Because as you go around the ring, you have to go around the ring, and so it's a periodic boundary condition, and then he said, well, we have periodic functions, and so we must be able to describe this function of temperature in terms of just periodic functions, and so I think that's a pretty interesting way to come back and say, how, well, rearranging function information onto this sum over transcendental functions has its root in thinking about periodic boundary conditions.